Welcome to Snap's Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about reliability prediction. This topic is based on a tech blog with the title Estimated Time of Arrival Reliability at Lyft, written by their machine learning engineering team. You can find the blog link in this episode's description. Throughout this episode, we will dissect this topic from both business and technical angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Ride-sharing companies, such as Uber or Lyft, have transformed the transportation industry by seamlessly connecting passengers with drivers through their on-demand platforms. Their apps provide quick and reliable transportation, which makes them indispensable in today's fast-paced world. The success of ride-sharing companies relies heavily on delivering a smooth user experience, which includes offering accurate and reliable estimated time of arrival predictions. Estimated time of arrival, or ETA in short, is crucial because it sets user expectations, helping them to manage their time and ensuring that rides are well coordinated. ETA reliability is a key to building and maintaining trust in a ride-sharing platform. When users can consistently depend on the app's ETA predictions, they feel confident in planning their schedules around the service. However, on the other side, if there were big variations in the provided ETA, it would erode customer trust, leading to ride cancellations, and ultimately users might leave the platform. This is why ride-sharing companies like Lyft are heavily investing in improving their ETA reliability to enhance the user experience. With the business problem now clear, let's dive into the technical side and explore how Lyft machine learning team is tackling this challenge. We will approach this problem from two angles. First, how to define the concept of reliability of ETA, and second, the technical solutions involved. On the first angle, to define the ETA reliability, we must first understand the product details. When a user opens a ride-sharing app, they see an ETA before requesting a ride. This initial ETA provides an estimate of how long it will take for a driver to arrive, and this gives the users confidence in making this request. After the user makes the request, the backend system dispatches a specific driver, and now a new and more accurate ETA appears on the screen. This post-request ETA is generally closer to the actual arrival time because it's based on specific driver's information, where the pre-request ETA is less precise because it lacks the concrete data about that particular driver. With this product understanding, the team defines the ETA reliability as the likelihood that a driver will arrive within a reasonable time frame around the pre-request ETA, if the ride has been booked. For example, if a user is presented with a pre-request ETA of 5 minutes, how likely would the driver eventually arrive between 4 and 6 minutes? This likelihood is represented as a score between 0 and 1. The pre-request ETA is particularly important because it is a key factor in user decision-making. The team also conducted analysis and found a clear relationship between the ETA reliability defined in this way and the user cancellation rate. As the ETA reliability decreases, they observe the cancellation rate increases. This finding underscores the importance of maintaining ETA reliability above a certain threshold so that it can positively impact the business. After defining the ETA reliability, now we can look at the second angle about the technical solution. At the core of this architecture system is a machine learning framework designed to predict ETA reliability. And this system composed of several key components. At the system product level, the machine learning model can predict the reliability of any ETA estimates when a user opens the ride-sharing app. The team established a stringent service level agreement for each ETA estimate, and they have the product team to strictly follow these service level agreements, typically requiring the reliability score to be exceeding a specific threshold. And this agreement ensures that only ETAs meeting this reliability threshold are presented to the users. This directly connects the ETA reliability service to the product the customer will experience. Then we look at the machine learning model itself. The machine learning model itself is a tree-based model. More specifically, it is using the gradient boosting trees. These models have historically been favored at Lyft because of their clear interpretability, the efficiency with smaller datasets, and the robustness to outliers and missing values. If we dive a little bit deeper into the model, there are features and labels. The features used in this ETA reliability model captures as much marketplace uncertainties as possible at the time of prediction. This includes nearby driver information, historical data at this specific regime or zip code, and real-time neighborhood demand and supply indicators, such as the nearby Lyft apps open at the moments. All of this information provides the signals about the estimated waiting time for this user request. On the label side, the team generated the training data by comparing the actual request to driver arrival time against the pre-request ETA. This creates a binary label for the ETA reliability model. One unique aspect of their approach was that they trained the model on all possible ETA estimates for each ride, rather than relying on only those who shown to the riders. For example, if the user is eventually presented with the pre-request ETA of 5 minutes, in the training process, it not only using this single 5 minutes ETA, it also uses all the possible ETAs to be presented to the user at this request time. This strategy helps avoid negative feedback loops during training and ensures equal representation of all possible ETA estimates during the inference time. In addition to the features, labels, and training processes, the team has also put significant effort into maintaining the model's performance during the deployment time. This ensures the consistent results being offered over time during a dynamic ride-sharing environment. With this business problem clearly defined and the machine learning system well integrated into production, This approach provides a reliable way to ensure a trustworthy user experience when users see the ETA on their ride-sharing app screen. Now we discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we discussed the importance of ETA for ride-sharing apps and the challenges of providing a reliable ETA to users upfront. We delved into the practices of the machine learning team at Lyft, examining how they developed a solution to address this unique challenge using a lightweight machine learning model. If you like the content of this episode, please subscribe to the channel, give me a 5-star review, and leave a comment. Your feedback is very appreciated, and I'll see you next week.